Okay, let's get things going. So it is my pleasure to introduce Sam Factor, though of course it's really much of an introduction in this crowd. Sam joined us here at UT from Wesleyan University, where he was in their joint BA/MA program and got BA degrees in physics and computer science and an MA in astronomy, if I got the right combination of them. During his time at UT, he's been awarded a year-long grad school continuing fellowship, and as well as no less than 3 successful Hubble and JWST archival programs that have made the advisor's job at least very easy, this whole process on that side of things. So today he's here to tell you about the research that was supported by all of these awards. This project started as a discussion between us about a new and sort of underused, underexplored idea in how to think about observations and how to exploit them to open up some really new, exciting scientific frontiers. And so now Sam has taken that starting point, developed one of the few platforms for basically analyzing data, not just as images, but really thinking about how does our data get produced in the telescope and how can we use that to really get the most out of it and making discoveries that other people, such as say their thesis advisor analyzing the same data sets, didn't get. And I've also learned a lot about telescopes and observing how our field works technically over this time, as well as learning a lot of interesting things and seeing some exciting discoveries about brown dwarf binarity and the formation of low mass objects. And I'm glad you now get this opportunity to share that with you. So, Sam.
Thank you very much, and thank you all for coming. From that intro, I have a lot to get through, so let's get right to it. So reading my title, you probably have some questions. Hopefully they're these questions, because that's what I'm going to actually talk about. And I'm actually going to answer them right up front, so you know what to look for as I go through my talk. So why interferometry and what is a kernel phase? I'm talking about kernel phase interferometry for the detection of close-in companions. Interferometry really enables us to do these very high resolution imaging studies. And a kernel phase is an observable, so something that we calculate from our data that is independent of wavefront errors that would cause this blurring that you see in regular imaging. So what did I do with it? I did 2 big kernel phase interferometry surveys analyzing archival Hubble Space Telescope data and demonstrating the technique on a new camera for the first time at the shortest wavelength that it's ever been used at. So the first of these 2 studies was looking at old field brown dwarfs. Some of these images had been previously analyzed with kernel phase interferometry, so it's not surprising we didn't find anything new, but that doesn't mean we can't learn something. And then the second survey that I did was on low mass objects in a young star forming region, which Adam actually analyzed using a different technique, which is what he was hinting at before. And this work is still a little bit preliminary, but we have 6 new candidate companions from that data set. So stepping back a little bit, what can we learn from this? I have these 2 catalogs. I can look at the population demographics of what we actually looked at. And we see kind of trends that were previously known, but we're now looking at them at different scales. So a decreasing trend of companion fraction as a function of primary mass, and a strong preference for tight binaries of equal mass objects at this low mass end of brown dwarfs. And then from the bigger picture, taking another step back, what does this tell us about how they form? And that comes down to turbulent fragmentation, which I will talk about in a second, setting the initial conditions, and then followed by a brief but very important period of dynamical evolution, which kind of shapes that initial condition. So getting right into the details here. Why interferometry? Yes.
I know which computer side.
Probably this one. Go away. There we go. Okay, so why interferometry? To answer this question, we actually have to start at the end. So what's the bigger picture? What are we actually trying to study? And that is brown dwarfs, and specifically brown dwarf binaries. and planetary mass companions. So what is a brown dwarf? I'm just going to talk while the simulation goes, and it's a little bit chunky, unfortunately. So a brown dwarf is the lowest extreme end of star formation of stars. They're a few percent the mass of our sun, and we can kind of use them as analogs for giant planets. And also it's very important that we understand these because they're very, very common. Like most of our nearest neighbors in our solar neighborhood are brown dwarfs. They're not actually stars. So unfortunately, simulations like the one that you're looking at right now don't currently have enough resolution to definitively answer how these things form. They just don't. You need way too much calculation resolution to actually simulate the physics on the scales that these objects form. But what you're seeing here is kind of a broad, very large scale simulation of turbulent fragmentation, what I was talking about earlier. So this is a big cloud that collapses down under its own gravity. It starts to fragment into little cores, which then continue to fragment down and go on to form stars. If two cores fragment close enough, they may become bound, and we get a binary. So that's one mechanism that these could form, just regular top-down, kind of like stars, but the lowest mass extreme. Another way that they could form is through disk collapse. So this is the same simulation on the previous screen, but now looking at cutouts of each of the individual stars as they form and zooming in very tight. And you can see that these baby proto-stars, proto-brown dwarfs, are accreting gas. And if there's a little bit of rotation on large scales, conservation of angular momentum tells us that that will transfer into a large rotation on small scales and form a disk around these stars. And inside that disk, you can have more fragmentation and form companions, whether that's planetary mass, giant planets, or low mass stars. Another thing that you will notice is that these things don't form in isolation. There's lots of stuff going on inside this cluster. And I apologize for Zoom making this video so choppy, but you can see lots of examples of interactions that would sculpt the population once it forms, and potentially disrupt binaries that may have initially formed. So unfortunately, when we go out and try and study these things in the real world, we can't just point a telescope and watch this happening. You can see the time scale is 200,000 years of this simulation, and clearly it's not done. There's plenty of action still left to go. So when we go out and we look at these star forming regions, we just get a snapshot. And we have to look at different star forming regions that have different ages or the field, which is very old, and try and draw statistical trends. And in my opinion, the best way to do that, the best technique, is using direct imaging. So we literally just go out, try and take a very high resolution image of a star or brown dwarf and look and see if it has a companion. And the poster child of this technique is the HR 8799 system. So this is a 4-planet system. These are all giant planets, many times the mass of Jupiter. And it's been observed for over a decade now. And you can really see Kepler's laws in motion. The inner planets are moving farther than the outer planets. And this really shows one of the strengths of direct imaging is by observing for these long periods of time, we can start to fit orbits to these objects and measure their masses dynamically using physics, Newtonian laws. And we don't have to potentially rely on simulations and models, which have ambiguities. So that's a big strength. The other strength is that we're actually resolving out light that is directly coming from these planets. And we don't have to worry about confusing signals of light that might be coming from the star versus the planet for transit spectroscopy. And we can do spectroscopy directly of the planet. And this can help us learn about the atmospheres of these planets, their compositions, and how they formed. So direct imaging isn't all just a rosy picture. Obviously, it has a lot of strengths. It probes these large separations, which other techniques are insensitive to, transit, spectroscopy, those sorts of techniques, much more sensitive to close-in companions. But as we try and push that inner working angle of direct imaging to closer and closer separations, we hit this limit that is set by speckles. And you can kind of see this in this image as these bumps and wiggles in the background that is caused by light interacting with either the atmosphere or our telescope. And those features happen on a scale that is lambda over d, the wavelength that we're observing at divided by the diameter of your telescope. And that's just diffraction. So that kind of sets this limit of how close you can go. If you want to go past that, we can use a technique called interferometry, which instead of treating those speckles as noise, we can, and subtracting them off, we can try and interpret any information that they have about what the light is, the shape of the wave of light that is coming into our telescope. And the way that you do that is interferometry. The classical way of doing this, using a technique called non-redundant masking or after-masking interferometry, is severely flux limited. The technique uses a physical mask that you put in the light path of your telescope that turns your 8-meter class telescope into an interferometer, but in doing so, it blocks out more than 90% of the light that is coming into your telescope. So you can really only do this with bright targets, or you have to invest a lot of telescope time, and you have to have a specific type of instrument that has a mask. And this is where the technique that I use, called kernel-phase interferometry or kernel-phase analysis, comes in. This allows you to get that really high resolution sensitivity that interferometric analysis gets you, but without using a mask. You can do this on the full aperture of your telescope, full unobscured aperture. Meaning you can do it with a wide variety of instruments, and you can do it for much fainter targets. So, kind of wrapping up that, kernel-phase interferometry is going to allow us to push our detection space to closer and closer separations. Hopefully we'll find something with it, increase our number of detections. And because we don't need that specific observing setup, we can use archival data to go back in time and potentially see orbits of these objects, or if something has been discovered recently, we can go back and try and find it in the archive. And with all of this information, we can assess the populations of these binary brown dwarfs and planetary mass companions, try and learn about their formation mechanisms at separations that you couldn't do without this technique. So, what is a kernel phase? This is the bane of my existence or the love of my life, depending on how you want to go about it. So starting off, very basic interferometry. Some of you might recognize this as a Michelson interferometer. This is kind of your basic physics interferometer. You have an incoming light source. It gets split into two different beams that then come back, combine, and are detected. And this, you can use this setup to very precisely measure differences in the path length, because as the light comes back, it acts as a wave, and it either constructively or destructively interferes on your detector based on very small path length differences. Now, this in this setup is used to detect gravitational waves. You can use it in instrumentation labs to very precisely measure surfaces of, say, gratings. But conversely, if we already know the path lengths very precisely, we can use that information, the interference pattern that we get on the detector, to learn about the source of the light rather than the instrument itself. And this is how we do interferometry in astronomy. So our interferometer, our different beams, are sections of our primary mirror. Different areas of the primary mirror have slightly different path lengths as they interact inside the instrument and then go on to making an image on our detector. And that path length changes as a function of position on your detector. And whether it's constructively or destructively interfering creates a diffraction pattern that tells us about the phase of the incoming light, which we're interested in because it allows us to get these very high resolution images. And the way that we take that image and get phase information out is by using a Fourier transform. So this allows us to convert all of that information in the image into spatial frequencies. And so in a very simple setup, I'll build up to the equation on the top. We have two different apertures here, and you can see there's some incoming light and a phase offset that we can measure either by passing it through an interferometer like you would in a, say, the very long baseline interferometer, or by making an image and taking the Fourier transform, we can measure this phase offset. And that quantity is dependent on the angle of the incoming light wave. So that's the quantity that we're actually interested in. What is going to tell us about the source that we're looking at? But unfortunately, these systems aren't perfect. And they also have some intrinsic offsets inside the instrumentation that is going to add a little bit of noise. So what we actually measure is a combination of what we want, that astrophysical phase offset, and the difference between these aperture-wise error terms. So abstracting a little bit, when we actually do this in real life, we take more than one observation. We don't just have two. So this is, again, a very simple example. So we have that same equation, but now we've measured it 3 different times on 3 different baselines. And to simplify the notation a little bit, you can stack those equations, make a vector and matrix equation, where on the left we have the information that we actually measure, the phase offsets. And then on the right, we have its components. What we're after, that phi naught, that's intrinsic to the incoming light, and then the error terms, and a matrix that encodes how the baselines line up to each of the apertures that have those error terms. So we're after something that gets rid of this error term. And in this very simple case, it's fairly straightforward. We can create a matrix that when you multiply it by A, it zeroes it out. And with 3 baselines, as I said, it's relatively straightforward. I've done all the math for you. If this will advance, there we go. And it's just one, in this case, kernel phase, closure phase, where we add or subtract the different baselines, and we take 3 measured phases and get 1 closure phase. And in this, again, in this simple case, there's actually geometric representation, where if we reverse the direction of the first baseline, we now have a triangle of baselines that make a closure phase. And this you can kind of think of as each of these has a positive error term and a negative error term. And when you sum up over a loop, they self-calibrate out. Yes.
So just to clarify, you're using the spider and secondary mirror as your mask here.
So the mask I'm simulating it on the primary mirror. I'll get to that in a second.
Okay.
There is no physical mask. Yes, there are obstructions, but there's no mask. Yeah, so we're summing up over a triangle, and we get this kernel phase or closure phase in this case, because it's a loop that self-calibrates out. Now, again, in the real world, this is a little bit more complicated. We don't just have 3 baselines. We have a mask that has, say, 9 holes, 12 holes. JWST has a mask. And we do the exact same math. It's just a little bit more complicated. The matrices are bigger, but we're doing the same thing. We have these triangles, these loops of baselines that self-calibrate out. Now, we can actually abstract this one level further and take away the mask. The math gets a little bit more complicated, but you can just trust me here that we're doing the exact same thing where we're finding linear combinations, no longer restricted to just 3 and no longer restricted to summing. You can also subtract, and we have weights on all of these now as well. So unfortunately, that means that there isn't a nice geometric representation, but we can still kind of look at it. So this is the visual representation of 16 different kernel phases, and the weights that you're seeing are what we would multiply each of the baselines by to self-calibrate out those error terms. So a little bit abstract in the last step there, but it's relatively simple at the most basic terms. So kernel phases are these phase-like observables, which are independent of errors introduced by the telescope, so they self-calibrate out. And they're calculated using this linear transformation, a matrix, based on the geometry of either your mask or your simulated aperture, your simulated mask on your aperture. So hopefully I've convinced you that this is not just all black magic. Don't worry if it doesn't make complete sense. It took me a while to get around this as well. But it's not magic, I promise. Just linear algebra. So what have I actually done with this? As I said at the beginning, I've done 2 different surveys with this technique. The first is a very large archival survey looking at nearby brown dwarfs using the NICMOS camera on Hubble Space Telescope. And these are all old, nearby, as I said, brown dwarfs. So this is not the exact sample that I'm looking at, but a representative sample of something that would be included in this. So we have 114 targets in the entire NICMOS archive observed in the 2 filters that were most common. And again, observed with a multitude of different programs, and I'm analyzing them all in a uniform fashion. So how does this actually work in practice? The first thing we do is we model our aperture. So in the background here in black, we have the primary mirror of the Hubble Space Telescope. And then on top of it, we plop down a bunch of simulated sub-apertures. And this is going to be our interferometer. We can then calculate all of the pairs of baselines or pairs of apertures to get the baselines. And that's what the baselines actually look at. Now I've color coded it by redundancy here because very short baselines are everywhere on the telescope. The longer baselines are more unique. And from this, we can get our A matrix, we can get our K matrix, and we can start actually doing some kernel phase interferometry. And that is where the data comes in. So I'm showing here a kind of obvious, though not easy for PSF fitting binary. And the image on top, and then the Fourier amplitude and phase. The amplitude we don't really care about for this technique. The phase is where this technique applies. And you can see this kind of step function in phase information, and that's the signal of the binary that we're after. So again, this is pretty obvious, but for other targets, it's not nearly so. We can then sample our phases at the baselines that were defined by the aperture model, and then multiply that vector of phases by our kernel phase transfer matrix. So this takes a large number of phases and gives us a slightly smaller but less noisy number of kernel phases that we can then fit a model to try and tell us information about what the source looks like. So this is an example. Slide. There we go. An example of, again, a pretty obvious binary here, 180 milliarc seconds. So that is about lambda over d. You can see that it's right at that first diffraction ring, the companion. And I'm fitting these kernel phases with a pretty simple binary model that is just the separation, the position angle on the sky, and then the flux ratio, the contrast ratio, in this case in 2 different filters, f111 and f170 W and M. So these are about 1 and 1.7 microns in wavelength, so near infrared. And this is, again, not easy, but pretty trivial, relatively easy for PSF fitting. But something like this is pretty much impossible to detect with the classical image analysis technique. So this is a 60 milliarc second binary, so that's about half lambda over d, less than half lambda over d, at a contrast of about 2.5. And this is there, at least I'm saying it's there. And there's no way, this doesn't show up quite as well as I would like on the screen. There's no way that you could just look at that PSF, that image, and say there's an image, there's a second target there. But the strength of this technique is there's enough information in all of these little bumps and wiggles in the diffraction pattern to tell us that there are two sources there.
So you're for modeling the PSF based.
I am not forward modeling
You're not
anything.
forward
I'm extracting all of the kernel phases out of the image and then just fitting those. There is a way to do it where you can forward model, but I don't do it that way. Yeah, so basically I've extracted kernel phases and fit a binary to all 114 targets in my sample, but not all 114 are actually binaries. So we need some way of determining what's real and what is noise that looks like a binary signal. And that's where detection limits come in. I don't have time to get into the nitty-gritty of how we actually calculate this, but ask me if you're interested. So this is showing where we can actually trust that a detection is real and where we can't as a function of separation and contrast ratio. There are two filters, and then these are just zoom ins on the very tight separation regime here. So once we have this for our entire sample, we can score our fits, our binary fits, as real or not. And we get a catalog of detections, and we get our survey sensitivity, which is very important for the next step. So yeah, we found 19 companions. That's what these black dots are. These were previously known companions. And then we have a few non-detections, which I can explain out as odd circumstances where either this technique doesn't work quite as well, or the data was low signal to noise. And importantly, we recover one of these high confidence previously detected with kernel phase detections, and that was that 60 milliarc second binary that I showed before, and that is right here. These are all previously proposed candidate companions that we did not detect. So yeah, as I said, 60 milliarc seconds out to about half an arc second with relatively significant contrasts. So as I said, I did 2 of these surveys. The second was on observations of Taurus and Upper Scorpius. And this is actually a data set that Adam looked at using PSF fitting back in the day. So this is a slightly or much smaller number of targets, 34, with again, some known binaries, and demonstrating the technique on the Hubble Space Telescope ACS, Advanced Camera for Surveys instrument, which had never been looked at using kernel phase. And there's some quirks of that camera. Again, I don't have time, but you can ask me about it later if you're interested. So again, kind of similar analysis. The pupil looks a little bit different. It's rotated 45 degrees, but we construct our aperture model. We measure all the baselines. From here, we can get those matrices, and we can start looking at data and fitting models. So again, this is kind of a representative observation of, now you can see we're in the visible wavelength. So the filter 555W, you can kind of think of that as 555 nanometers. So the wavelength is much shorter, meaning the diffraction pattern is much shorter, and you can start to see these things down to 36 milliarc seconds. This is again like half lambda over d, so nothing trivial here. But the wavelength is smaller, so it's a little bit easier to get down to those very, very tight separations. And we have 3 filters in this survey. So this is 555, 775, and you can see as I scroll, the PSF is going to grow a little bit as the wavelength gets longer, diffraction pattern gets bigger. And also you can see some of the quirks in the detector in the longest wavelengths. So again, calculate detection limits. This is where This survey is a little bit preliminary. Those detection limits take a lot of computation. So they're not all done, but we can still use the ones that are done to infer what may or may not be real binary detections. So again, we have 3 different filters. There's some interesting differences between the sensitivity of the different filters, which again, ask me about it if you're interested. We recover 4 out of the 5 known companions. That one that is not detected is this red dot here, the blue are the known. And more recent observations have put this a little bit lower, meaning it's brighter. And oddly enough for this technique, that makes it harder to detect. Ask me about it if you're interested. So yeah, we found 4 out of the 5 known companions, and we have 6 candidate new binary detections. All of them are really tight separation. 1 or 2 of them might be a little bit marginal. We might lose them in the final detection limit run, but it shouldn't change the results by very much at all. So yeah, going back to the outline here, I have these 2 catalogs of detections and sensitivity where I looked for them, but I didn't find anything. And we can try and learn what is hiding behind that sensitivity. What is the actual population that we looked at? And this is where the demographics come in. So again, I'm going to do that same kind of parallel analysis on my 2 different surveys. For the field old brown dwarf, I had to restrict down the target selection to just programs that were unbiased surveys looking for binarity. There were a few that were targeted follow-up. We know this is a binary, we want to get some data. And if we want to look at the population, we have to have an unbiased survey. So that's why it's 105 targets and 15 binaries rather than 114. Yes, so the first step in looking at the actual population is converting our observed parameters into physical parameters so we can learn about those systems. The easy one is converting our projected separation. So in an image, you see the angular separation of that binary into a physical separation. And that's just regular trigonometry. We take the angle, we multiply by the distance, and we get the physical separation. In this case, the distances come from Gaia and some of Will Best's very important work on brown dwarf parallaxes. Getting the mass or mass ratio from the observed contrast ratio, how bright these things are, is a little bit more complicated, but we basically just use an evolutionary model. But importantly, for this old population, one of the parameters that goes into the model is age. And because we're looking at field age, old population, it's not very well constrained. Also, because these are just out there, it's probably a mixture of younger and older brown dwarfs. So I ran the whole analysis for a set of ages so that we can get around that. So this is that same plot that I showed, the summary of our survey sensitivity in the background and our detections in points, now converted into physical units. So separation in AU and mass ratio, just the ratio between the primary and the secondary. And I'll scroll through here for the different ages. You can see about 1 billion years up to 3 billion years is our oldest. And as we get to older and older ages, these things get to more equal mass systems. That's just because hot things cool off faster than cold things. And so they tend to get closer in mass ratio. So we have this where we found things and where we could have found things, but didn't. We can now fit this with a population model. This is a fairly commonly used population model with 4 parameters: an overall companion frequency, so how likely is something to have a companion. This can actually be greater than 1, in which case it's a triple rather than a binary. We model the distributions in mass ratio and in separation as a power law, so Q to the gamma, and a log normal, so a Gaussian in log space over separation, which has a mean and a standard deviation. So putting that all together, don't worry about the equation, but this is the Gaussian, this is the power law, This is the overall companion frequency, and then we have some normalization constants out front. So this gives us the predicted rate of binarity with a given separation and mass ratio. We can then plug that into a likelihood function. In this case, we're using the binomial distribution. We have a choice. Does it have a companion? Does it not have a companion? And then that rate comes from above, and then we have the number of systems that we are sensitive to and the number that we actually detected. And this we can use in a Bayesian inference algorithm to get out our posterior distributions of this 4-parameter fit. So I actually ran this twice. I'll explain why in a second. But for the first pass, just look at the blue posteriors, the no prior. And some things that you'll see is the overall companion frequency. Don't worry about the titles, that's for the orange distribution. The overall companion frequency is very unconstrained and also very high. It's greater than 1. And the other interesting fact is the separation distribution. The mean of the separation distribution is very tight. It's like less than 1% of an AU, which is about the size of a brown dwarf. So something is going wrong here. These things would be crashing into each other if they were actually on these orbits. And we can see that when we look at our observed companions in blue here as a function of separation. Now I'm plotting over the best fit model in solid black and a distribution from the posteriors in orange. And the model is basically saying there are a bunch of unresolved binaries that are below our sensitivity. Because our observed companions are right up against the inner working angle of our survey, we don't know whether a decrease in observed companions is due to actually there being less companions or just because we're not sensitive to them. And so the model is saying, we have no information out here, so see what happens. And this isn't very feasible. Luckily, there is information that we actually have about the companion distribution down here. And that comes from a radial velocity survey that constrains the binary fraction of systems less than an AU. So 10 to the 0 right here, which is exactly what we want. And this is that orange distribution that I showed previously. When we plug in that prior into our Bayesian algorithm, we can incorporate all sorts of different sources of information, which is great about Bayesian. We can now get out a more reasonable posterior distribution. Again, our observations in blue, that best fit model in orange. Now I'm also incorporating a Malmquist bias correction. Don't have time to go into it, but ask me about it. And if you ever are looking at surveys of binarity, it's very important to account for Malmquist bias. But the main takeaway is that our simulated observed companion distribution, we take our best fit model, we apply that correction, we apply our sensitivity, goes right through all of our actual observed companions, because that tells us that this is not only a good fit, but actually physically relevant due to that constrained type separation distribution. So kind of the same thing, but in 2 dimensions now. I'm splitting out our sensitivity in the top right with the detections, and then that best fit model, again with our detections, and then what happens when we combine them into again, with that Malmquist bias correction, we can see the detections line up well with that best fit model. Great. What is this? How does this fit into previous analyses of similar objects? So this is those 4 model parameters again, but now plotted as a function of the mass of the primary in the system, in the binary system, or a multiple system. So this goes from masses, primary masses that are 1 solar mass, the sun, down to a few percent down into the brown dwarf substellar regime. And we can see that our results are roughly consistent in the trends with other previous analyses. The separation distribution is a little bit tighter, a little bit smaller than previous studies. That's because we're using this very high resolution technique. Even though we didn't find anything, we are still constraining where we could have found things. which allows us to put that a little bit lower. And then just general trends that we've seen is this decrease in companion frequency as you go to lower and lower mass. And then, as I said at the beginning, this strong preference for equal mass, a high mass ratio power law index, and tight separations. So just kind of some numbers to put on that. Less than 1% of these binary brown dwarf systems have separations greater than 20 AU or mass ratios less than 0.6. So they're very rare. So again, kind of parallel analysis of that other survey that I did. Again, we had to restrict our population a little bit based on what is actually known to be members of these star forming regions, so 31 instead of 34 targets. Again, convert those observed constraints into physical parameters, pretty much exactly the same as we did with the previous study, except because we're looking at young star forming regions, we now know the age very precisely, so we can use that. And that's thanks to some work by previous members of Adam's group. So again, kind of similar to the previous analysis, we can look at our sensitivity and our detections now in physical units with those assumed ages, and we can fit a model. And we hit the same hiccup that we did last time with that unconstrained total companion frequency and a relatively tight separation distribution. Unfortunately, with this sample, there really isn't an RV study of these sorts of objects that we can use to put a prior and restrict those unresolved companions. So in this case, I'm actually reporting 5 parameters, and this is our observed companion frequency. So what would happen if you take this whole posterior distribution, multiply by our sensitivity, and then integrate to get the number that you would expect to actually observe. And that's consistent with previous binary studies of torus and upper Scorpius. So again, showing that same plot we saw previously, our observed distribution as a function of projected separation. Again, we see that preference for unresolved companions. You'll notice the scale is a little bit different. These objects are much farther away, so we can only get down to a few AU rather than less than an AU in the field case. But there's really not much we can do about that unresolved companions problem, other than be careful when we compare them, that we're only comparing regions of parameter space that we actually have sensitivity to. So again, same thing as before, we have our survey sensitivity detections, best fit model. You can see that unresolved companion, but when we combine them to see what we would actually observe, it fits well to our detections. And summarizing that, we have our best fit parameters. Again, we see that same trends with low companion frequency, at least that we're sensitive to, and a strong preference for equal mass and tight separation. Our observed binary frequency is a little bit higher than previous analyses because we have those new detections, these candidate detections that Kernel-Phase has discovered, but within the error bars, roughly consistent. So, what can we actually learn from these two populations? Remember, we're trying to figure out how these things form. Simulations just aren't quite there yet to give us a definitive answer. So, these two surveys that I've done, the mature population, we can think of as the end state. How do things end up? The young population is the initial conditions. Again, as I mentioned, the mature population is very nearby, so we have lots of sensitivity down at the AU kind of scale, versus these young populations are farther away, so we're limited. This is kind of grainy here, but we're limited to a few AU. But it's still better than what we could have done with just regular PSF fitting. And then also importantly, as I mentioned before, this old population is a mixture between brown dwarfs that have formed in regions like Taurus and Upper Scorpius, these low density star forming regions, but mostly 90% of them have formed in high density star forming regions like Orion or even more massive regions. So we have a small representative sample of the young population and then a mixture of the old population. And because we have these detailed demographic studies, we can compare them. Again, we have to make sure that we're only comparing regions of parameter space that we're actually sensitive to. So in this case, I'm showing the companion fraction greater than 5 AU, where in the low mass or the young sample, we're 90% complete at 5 AU. So this is a pretty good region to look at. And you can tell that the companion frequencies are different. This is really cool. So the young population about 16%, the old population 3% with some error bars. So that's interesting. The other parameters are pretty much consistent. The mass ratio distribution is good within 1 sigma, but there's also that caveat of the old population. We don't know the age. There's probably a distribution of ages actually, but they're both high, so relatively consistent. And then in the separation regime, those are all consistent, well within 1 sigma. So what does this tell us about the big picture? So in terms of the general population demographics, that separation, mass ratio, and the overall companion frequency, this tells us that turbulent fragmentation is setting the initial conditions, rather than disk interactions or kind of odd one-off simulation situations where like triples are evaporating or something like that. Turbulent fragmentation fits well with the overall distribution. But we saw that difference between the old and the young population. And that tells us that there's some dynamical evolution that's going on. Specifically, we're looking at wide companions. So it prunes off those widest companions and leaves behind some population that then makes it to the field. Importantly, though, this dynamical interaction has to occur inside the birth cluster. Once these things dissolve and reach kind of the field distributed cluster, the interactions just aren't strong enough to actually dissolve these binaries. They're only strong enough to dissolve the very, very widest, which are very rare anyway. So it has to occur inside that birth cluster, which leads us to the conclusion that the star formation environment should have some impact. If there's lots of stars moving around, we should see that, versus in the low density, maybe there's less processing that goes along. So if we take that conclusion that the interactions have some, or the birth region has some effect on the interactions, we can create a toy model. So if we start with our old population, we have a wide companion fraction of about 1%. And if we make the assumption that only wide companions that are formed in these low density regions actually survive, and we say 100% of them survive, just for the sake of this toy model, 100% of those survive, we can then dilute that population that we know really well from my work on Taurus and Upper Scorpius. We can then dilute that population by the relative fraction of stars or brown dwarfs that form in low density versus high density regions. So we can take that 90%, assume all of the wide companions are removed, they don't survive, and so you only have single stars. We can dilute that, and we get a population that is consistent with our observed field population. So this is 0.5% with some error bars, consistent with 1%, again, with some error bars. But within 1 sigma, they're very consistent. And maybe that little decrease in our toy model diluted population, that might hint at some other things going on, maybe not 100% of these wide companions that are born in high density regions, maybe not 100% of them are removed, maybe some of them survive. pretty likely this 10 AU cutoff is not sharp. There's some range of separations where this is more likely to happen or less likely to happen, but it's probably not a sharp cutoff like that. So maybe we can eke some more information out of those numbers with some better statistics, more follow-up information. And that is my talk. I'll go through my summary slide and then tell you about what I am doing next. So hopefully I've convinced you that kernel-phase interferometry is a really powerful technique. It's not black magic. And then I have applied it to 2 data sets, one looking at old brown dwarfs in the field, one looking at young low mass objects in Taurus and Upper Scorpius. This included demonstrating this technique at the shortest wavelength that it's ever been used at, and preliminary 6 new candidate detections in that analysis. And then I analyzed these catalogs that I made and looked at their demographics, their binary demographics, and then connecting that young population to the mixed old population. We can tell that turbulent fragmentation is likely what sets those initial conditions of binaries. And then there's a very brief before that cloud dissolves period of dynamical evolution, which depends on that star formation environment. So the high density regions process more than the low density regions. And that makes sense from physics. So what is next for me? As Adam hinted, I am very lucky to have had a JOC archival proposal accepted that will fund me as a postdoc. So I'm just going to stay here and apply this technique to the next generation of space observations and try and use these detection limits that I can calculate to figure out what are the best practice observing strategies to get the most out of this technique on this new camera. And also I want to just say a big thank you to all my colleagues, classmates, and friends in the department. One of the main reasons why I came here to UT was because I could tell that the grad student population was not only relatively happy for being in grad school, it's a stressful time, but very supportive of each other. And you guys did not disappoint, and I hope that you continue that tradition of making UT Austin a very friendly grad student community. I also want to shout out my teammates at Synchronicity. We like our rowing puns at the Austin Rowing Club for getting me up in the morning. Rowing has been a big part of my life for a long time now, both keeping me fit physically and mentally, and also my one wheel, because that thing is just so much fun, and it was a great use of my time during pandemic when I couldn't have too much interaction with other people. So yeah, thank you very much. I will leave up my conclusions. We'll advance here and take your questions.
Okay, great. So as a standard, committee members, just hold your questions, you will have your opportunity. But if anybody else has questions, then feel free, and I'll watch on Zoom and see if anyone raises hands there.
I threw some your way during the talk, so hopefully. Yes.
So is this technique, like, do other people use it, or are other people going to use it?
Good question. Yes, there are other people that use it. The community is pretty small at the moment. I have a whole paragraph in my dissertation that lists out all of the papers, and there aren't that many. But yes, it's been used, as I mentioned, this analysis of field age-bound dwarfs. There was a paper on that I replicated on a larger sample. That was kind of the main one. And then it's been done from the ground a few times from the BLT and on KEC. And on JWST, there were a couple actual observing proposals that are using the technique, as well as my archival proposal. So yes, other people use it, not very many people though. So hopefully I can open the doors a little bit and clean up that black magic misconception. Yes.
Yeah, I had a variation of Kyle's question, so you're clearly looking at star formation and binaries around where. But the KPI seems like a very powerful.
Yes, absolutely.
technique. I'm just curious to know whether people have used it in other fields entirely of astronomy to do interferometry, if anything.
I don't believe so. Most of the like high resolution imaging community is focused on like planets and binaries. So I don't think anyone has actually applied it to say like looking at supermassive black holes like point sources. It's easiest to do this on point sources, but there's nothing saying you can't do it on non-point sources. But yeah, that would be a great application. Yeah. One caveat that you need to be aware of is because we're using phase information, you have to have, you're insensitive to symmetrical image plane features. So that's why binaries, there's that turn down in sensitivity to equal brightness at close separation. Because you lose that asymmetry, you lose some of that sensitivity. But if you have asymmetric features, you could absolutely use this technique.
I've got a revelation for you. Nothing in astronomy is truly symmetric.
Absolutely, absolutely.
No spherical cap.
Yep. Yes.
So in your ACS slide, why a wider containing make it more difficult?
Yeah, so that was kind of what I was getting at before. Let me just go down to, we'll go here. Yeah, so why does this companion, when it actually got brighter, lower contrast, make it harder? So that's this turn down in sensitivity is that loss of asymmetry. So equal brightness companions very tight, the phase signal is flat, pretty much. So we lose that sensitivity, whereas if one of them was a little bit fainter, you gain that asymmetry back and you can see that in the phase. So yeah, and this thing has been confirmed. Adam followed it up with some NERC2 imaging, and that's where the information about it being a little more equal brightness comes from. Yes, Kai.
This might, great talk, Sam.
Thank you.
This might reveal my continuing challenges in understanding KPI.
That's what I'm here for.
I'm wondering how you decide, like what are some of the considerations that go into kind of the number and the size of the sort of synthetic apertures?
Yes. So there's a reasonable amount of thought. You'll notice in this aperture versus the one I used for my NICMOS observations, this actually has a transmission factor. So it's not just a black or white, transparent or non-transparent aperture. We're actually including some of that here. There's some considerations on the spacing of your apertures, just like with any interferometer that sets what spatial scales you are or are not sensitive to. So you basically have a window function based on whether or not you care about finding wide things or just close in. And obviously there's some trade-offs between having more sub-apertures, you get more kernel phases, makes the computation a little bit heavier, more data points. And somewhere along that, there's a trade-off between having more data points to fit versus them being just cumbersome, or you hit some noise scale in terms of like the readout noise of your detector or something like that. But yeah, those are the kind of broad strokes considerations. Yes, one last one.
Could this like be applied to like deconvolve an image? Like if I'm imaging a nebula and I look at the stars around it.
Yeah, so not particularly. I mean, there are ways of using in the radio domain of going from closure phase back to image, or in aperture masking, you can go from closure phase back to image. Because we already have like a diffraction limited image, we're essentially kind of doing that. We're just making some assumptions about what our source plane looks like in terms of point sources and constraints about what that looks like. I have a animation here, which I'll show really quickly. This is, someone tweeted this out, someone on the JWST ERS team. And it's just an animation of how the diffraction pattern changes with different features in your primary mirror. So obviously, like the diameter changes the overall size, and then these spider arms have an effect there too. I tried making one for my simulated aperture model, and it looks a little bit funky. So hopefully this doesn't get too confusing. But when you have these grids, you have this symmetrical features in your simulated PSF. So we don't actually, obviously, we don't see a PSF that looks like this. But if we were to observe with a interferometer that looked like that, this is what we would see. So this is kind of from the radio side of things, your dirty beam, if you will. So we have sensitivity to different regions. So kind of that answers your question. This is what our PSF would look like, but all of the analysis that I do is on the Fourier side of things, not on the image side. Yes.
So thinking about JWST's PSF, it's like horrendously complicated.
Yes.
So like, what are the things that you're most worried about moving forward with your archival thing? Like, how is this going to translate?
Yeah, so people have done this technique on segmented mirror telescopes, on Keck and on JWST. Jens Kammer, who's another member of the community who uses this technique, is on the he's at Space Telescope. So he did a paper on the using Kernel-Phase. So what am I most worried about? The segmented mirror is not that worrisome to me. You can just put down your apertures where there's light coming through, and it should all work out on the back end. Some of the things that I'm interested in experimenting around with are maybe sun angles, how that segmented mirror is going to change with time, with angle of the sun, with micrometeor impacts. The good thing though is they do a lot of tracking of that information, of wavefront sensing. So having that other data set to go along with this would be very informative. So yeah.
Well, we are a little past 5, and so with that, let's thank Sam again.